This lesson is going to look into power. We've probably heard of a horsepower before, and this goes back to some experiments done by James Watt, who was an engineer from Scotland, and he did lots of exploration, and he measured how fast a horse could lift weights. So he's got this 550-pound weight, and he knew that a horse could lift it 1 foot high, and it took him 1 second to do it. And he called this a horsepower. Well, that's the old empirical units that we're not going to use. So if you hear of a horsepower, you can convert it into the metric units or the SI units that are called watts, named after James Watt. So power is the rate at which work is being done. So in other words, power is equal to the work divided by the time. Or we could say it's the energy being divided by time. Because remember, there's work and energy are very connected concepts. So work and energy divided by time. Let's look at the units here for a second. If we remember that a work unit is in joules. And if you remember that the joule, 1 joule, was 1 kilogram meter squared per second squared. So now we're going to take that and we're going to divide it by our time units. Once again, time in seconds. So the units here for power is going to be 1 kilogram meter squared per second squared per second, which is a kilogram meter squared per second cubed. And that is 1, and it's named after James Watt, 1 watt of power. Let's practice solving a couple questions. All right, so you came into school and you set your book bag on the floor and you opened up your locker and you took your book out, and it's got a mass of 1.1 kilograms. And then you're going to set that up on top of your locker here. So you're going to put your book up on top of your locker. Okay. And so it was here, and now we're going to move it to there. And it's got a height of 1.8 meters. And we did this in a total of 3.2 seconds. That'll come back in a moment. The first thing we need to do here is we need to either calculate the work or the work done or the energy used to do this. Okay. Well, basically, we're looking at the amount of work done is equivalent to the amount of energy we've given this system here, because this now has potential energy. The book up on top of the locker now has potential energy, which is mgh. So the work done was the work to give it this amount of energy. Okay, so it went from having 0 joules of energy, and now we've raised it up. Okay, so what's its potential energy now? Well, it's going to be the mass. So it's 1.1 kilograms multiplied by gravity, 9.81 meters per second squared, multiplied by the height that we moved it, which was 1.8 meters. So it now has potential energy of, let's see, 19, do that math, 1 times, it's almost like 1 times 2 times 10. It's just going to be a little bit less than 20. I'm seeing 19.4 0.4238 joules of energy were used to raise that book. Okay, so that's the work that was done. So now I know that the power is the work divided by the time it took to do the job. Okay, so that's not so bad. So the power is going to be 19.4238 joules divided by the time. And the time in this example was 3.2 seconds. So we know that the power used to move that book was 6.07 watts. Now I do want to remind you that this is a watt of energy, watt of power. This is the symbol for work. Be very, very careful you don't get the watts and the work intermixed. They're very different things. Let's try another example. So you get up in the morning, get ready for school, and you leave the bedroom light on, and you're gone for 6 hours. And let's just say it's only a 60-watt light bulb. I want to know, how much energy did you just waste while you were too lazy to turn off that light? Okay, so let's see. Our power is the, I was going to put change in energy, or the energy. I'm going to get rid of that. Don't need that there. Okay, so our power is energy divided by time. So little algebra, we see that energy is the power times the time. Now this is going to be the whole problem. Lots of sixes in this one. So this is going to be the power, which was 60 watts, multiplied by the time. But we need the time in seconds, and we've got it here in hours. So be very careful you get the right units. So let's see, so 6 hours, and we know that 1 hour has 60 minutes, and we know that 1 minute has 60 seconds. So the time here would be 6 times 60 times 60. I see that as 21,600 seconds. And we'll use that right here. So just a day at school, and you left your light on in your room, and you have now used 1,296 kilojoules of energy, or 1,296,000 joules. Turn the light off, folks, and save some energy. Save the world. Save your parents some money. Okay. Here we've got a bike going to go up a hill. Okay, so here's my hill. Okay. Now, how did I know that was a right angle triangle? Well, I've got a hill. This is 400-meter hill. And I know that I've got a slope here of 30 degrees. And what I need to know is I need to know the vertical distance. The easiest thing really is just to set up a triangle to figure out this vertical distance, okay? This is what we're going to call the height. And we have to be really careful we don't get the height confused with the hypotenuse of our triangle. Okay, so I'm going to call this my distance so I don't confuse it with my hypotenuse. And the distance, and this we'll call the opposite with the hypotenuse there. Okay, so we know that the sine of theta is the opposite over the hypotenuse. So the hypotenuse times the sine of the angle must equal the opposite, which is the height of what we're doing here. So let's see. So this is going to be the hypotenuse. So that's 400 meters times the sine of 30. those of you in pre-cal, you've learned your unit circle and stuff. You know that this is a half, so this is going to be 200 meters. Okay, so our height here is 200 meters. Okay, so the bike at the top, there has potential energy at the top of the hill. And we had to do work to get the bike up the hill. Okay, so the potential energy is the mass times gravity times the height. So that's going to be mass of 65 kilograms times the gravity, 9.81 meters per second squared, times the height that it went up. Remember, it didn't go 400 meters. It went a vertical height of 200 meters. Okay, so the potential energy at the top here is going to be 127,530 joules. Let's see, is that seem about right? Let's see, 10 times 200, that's 2,000. Yeah, that sounds about right. Okay, so that's the potential energy at the top of the hill. Okay, and what's our power? Well, our power is the work done divided by the time. So that's going to be our power is 127,530 joules divided by, was it 72.3 seconds? 72.3 seconds. So our power here is 1771.25 watts, or we could say that our power is 1.77 kilowatts. I love those metric or SI prefixes, kilo.